So the prime field CTB square minus, okay, doesn't matter, yeah, GX. Square minus equals gamma square minus r gamma square Так. Ждем или что? А? Уже идет, да? Хорошо, да. Okay, so today's aim is to prove this statement, the number, how to calculate the cardinality of periodic points located on the elliptic curve. So I use this notation, Gx inside. So T is of course from Fp. Fp is a prime field defined for prime number P, okay? And as you see that this expression is totally correspond to the hypergeometric function series expression that we obtain for the periodic integral, elliptic integral I0. Okay, so no, this one is. That is say, so CT, this point means that we're looking for point x Fp such that x minus 1, so Gx belongs to Fp squared. No, there exists y such that y, it's evident, yeah. Look for. And we divide this Gx independence of the value of Gx, we divide x into three cases. The first one is Gx belongs to Fp squared, So in this case, gx to the power 2 p minus 1, p is of course odd number, so we can define this, equals, that is say, y to the power p minus 1, isn't it? That is say equals 1 by a small Fermat theorem. So second case is the case when gx fp but not square number. So what happens if you, for this case, gx to the power p minus 1 over 2, so if you consider power, the square, then it is g to the power gx, again it is 1 mod p. But it is not so. There are two cases. That is 1 or minus 1. But one case has been exhausted. That is, say, gx 2 over p minus 1, because minus 1. The third case is where so x equals 0, 1, or t. These. So 0 point, it's evident that gx 2 minus 1 equals 0 mod p. That is say, if I add, that is say, 1 plus, if I consider 1 plus gx p minus 1 over 2, this, now I add 1. I get 2, 0, and 1. 2, 0, 1. But as you see that, so this is, so fp, in this case, we have 2 such y's. That exactly this number correspond to the number of xy pair that satisfy this equation. The first one is we have two xy pairs. If I can say 1 plus this number, that is 1 plus minus 1, 0. This case, we have no such xy pair. And the third one is that we have only one xy pair, isn't it? Y equals 0. X, that is say, if I consider summation, that is exactly, so 2 times number 1 plus cardinality of case 3, that is exactly the cardinality of such of CT itself.
Is this equality of modulo P or?
Modulo P, yes. Modulo P. Everything modulo P, yeah. So to go further, so this is our first consideration. So first, to go further, I need to prepare a lemma that tells us that number of summation of x to the power k, if x n equals 0 mod p, if p minus 1 does not divide k, and the same expression is equal to minus 1 mod p if p minus 1 divides k. In fact, proof, so this can be seen. You consider this kind of expression, k, y, for y something, y any fp. Let us consider this summation. Then you see that it is y to the power k of this. Okay, let us call this expression somehow like some sk. That is yk times x, y to the power k times s to the power k, sk, isn't it? But this expression itself is already sk. Oh, so no zero. No zero, of course. P is prime, so it's cyclic. So, okay, sk, that is say 1 minus y to the power k, the power sk equals 0. That is say if y to the power k is not 0, then sk itself must be 0. Yeah. So if y to the power k 0 p, then sk is 0. This case, and y to the power k goes 0, 1. This case, but small Fermat theorem. Yeah. Then what happens? In this case, we need to be a bit careful. Yeah. So it's enough. Sorry, maybe this case, I calculate x. So this is p minus 1. Let us see. P minus 1. So it's summation of 0 plus 1 p minus 1. No, x to the power p minus 1. P non 0. There are p minus 1 such x, isn't it? Except 0, others. And from 1 to the p minus 1 to p minus 1 and so on, to p minus 1 to the power p minus 1, everything gives contribution 1, that is say p minus 1, this contribution. Yeah. This is what is written here, no? This is what is written here, yes. This is what is written here. Okay, this is lemma that I used to deform this expression. Now, to show this equality, so we go back to gx, this, yes, okay, I write it, equals, we establish this fact, 1 plus gx to the power p minus 1 over 2 x fp, all fp grounds over, that is this number. Yeah. So we need to calculate this, this expression. Now, independence of t. Independence of t. Okay? So gx that is, say, x minus 1, x minus t, 2 over p minus 1, isn't it? Or I can factor out this simple it is quite relatively simple. So this expression is a series, in fact a polynomial, yeah, that begins from the degree, this degree, x p minus 1 over 2. So it's something, yeah, what happens? Say kj, k to the power j, this power j, etc. But we recall that yeah. So this is, here you see, it's summation of, summation of j equals, in fact, from 0. Isn't it? I take that. So it's summation j kj times sj. But in fact, so maybe no, it's not a good, no, sorry. So no, sorry, no. No. Summation must be here. Summation over ft must be so x. So this is j plus 2 over p minus 1. kj times xj plus, yes, this one, this. And this lemma tells that if k is not, in fact, everything about p, it is enough to consider till p minus 1. Yeah, everything. So j, in fact, it ends at p minus 1. So the summation ends here. No. I already took summation, yes. That is a j plus that gives us the only contribution because of this lemma. Others vanish.
We have interchanges the sums. Where is the sum over x now?
Here, I introduced this notation sk. Summation over x over fp is so.
G is summation is a number that depends on g and t.
Yes, this number depends on t. Coefficient depends on t. Yeah, this is, here we have a summation. Okay, then only this part survives. That is, in fact, this is equal to k. Instead of j, we put b minus 1 over 2 t. Okay, to yeah, and sp minus 1 was p minus 1. Yeah, like this. That is, say it's minus. Oh, wait a minute. Whether I did something like this. Yes. Okay. That is say p more p. So it's minus k p minus over t. So we succeeded to express this expression that is present here, summation, in terms of some function t. No, not succeed, we simply reduce it. A kind of reduction. Okay. Now, in fact, k, but this nothing but the expansion of this expression, isn't it? So, yeah, and this expansion, I expand this expression like first factor x minus 1 to the power p minus 1 over 2. This will become p minus 1 minus p minus 1 r. It's simply binomial coefficient. In fact, because I have this factor, x to the power p minus 1, 2, it's enough to consider till p minus 1 over 2. Summation ends up at the step p minus 1 over 2. Times, so this is x minus 1 to the power, okay, to be clear. So this factor comes this, and for 2 L times minus t to the power L. The expression is absolutely parallel, isn't it? Minus L. Yeah. And this comes from here, x minus. This comes from here. Yeah. And consider summation. Consider summation.
So where is k here in this formula?
I will calculate.
So we are now writing down the expression.
Yes. So yeah, that's the point. You know, you're right. You pose yourself the right question. So it's the coefficient of x to the power p minus x to the power p1 minus over 2 of all this expression. Yeah? Coefficient of it. This will be our kp minus 1, this function, yeah, t, yeah. Okay? But as you see that the only, so we use lemma, maybe lemma, summation of x to the power k equals 0, k that was lemma. So that is say the only interesting term, non-zero term that appears in this situation is the power of such that r plus L equals 2 over p minus 1. Let's see, we have, it will give us the power so this factor, yeah, this term, and times x to the top power p minus 1 over 2. That is, in total, we get x to the power p minus 1 times something non-zero. Others vanish. Okay? That is, say, it's enough to consider in fact only r plus L equals p minus 1 over 2 that survive these terms. Then this can be expressed r L, and so if minus 1 minus t to the power L, isn't it? And minus 1, something is like a minus 1 to the power, what happens? Wait a minute. Minus 1 to the power r. Yes, r is so instead of r I put minus 1 to the power p minus 1, and so t to the power L, and minus 1 to the power r plus L. Minus 1 to the power r plus L, minus 1 to the power p minus 1 over 2. Okay? So it is this multiply by this factor, all terms, the terms. And this will give us, everything is mod p, some easy calculation. So our r is, our L is dependent, L is expressed, r is expressed by L, simply minus L. That is, say, this, if you divide it into only in L, then you get p minus 1 L square square t to the power L. Yeah, mod p.
The upper parts of the binomial coefficients on the previous line are wrong.
Which one?
The second last row,
Yeah.
the binomial coefficients on the upper should be p minus 1r.
Of course. Of course, of course. Nonsense. Yes. Yeah, thank you. So now this expression is quite near to this. Simply the difference of p, and it's enough to see that that this equals to this equals to this equals to this. So I have a minus 1 also here. So it will yeah, give contribution minus plus 1. So the comparison of two so minus, we have this is one minus one, etc. Minus, we have L minus L terms, P minus 1 over 2 L, that's what it is. This is you see what 2? And if you erase p everywhere, then we get, I think, that the same expression as here. Huh? In fact, this is also fp number. It looks like rational number, but there is no rational number in fp. This is number such that something that times L to the power n equals 1 mod p. That is the definition of this number. Okay. So this kind of procedure is legitimate. Okay. That is, say we get we see that if this is nothing but the power series expression that appear here. In fact, this is of course a polynomial. No?
So, have we proved the theorem?
Yes.
So the summation in the theorem should be from r equals 0 to pi minus 1 over 2.
Yes, yes, yes.
Not infinity.
No, not infinity, yes. It is finite sum.
And this is a congruence modulo p.
In fact, the definition is this. Definition is so that, in fact, not to talk about this, the limit of, because this function is 2 pi over 1 times pi t. Isn't that this integral? Oh, rather 2 times. So the point is that this so cardinality of periodic points on the elliptic curve is expressed by means of period. By period. That's the point. Yeah. So this, in fact, this is very small portion of what Manning did in his article. Yes, I was looking at.
So we have proved a different statement.
Mm-hmm.
We have proved some congruence modulo p.
Modulo p.
And this is just inequality.
Mm-hmm.
And the right-hand side is always an integer.
Oh, yes, this has been defined. Yeah. Yes.
Because it periods.
Yes. Yes. Pi pt.
And for which t does this theorem hold?
T fp. Of course. Otherwise, no meaning.
How do we do infinite sums over fp?
Fp, no, infinite sum it's a notational convention. So yeah, you are right. In fact, this is p minus over t. That's all. Yeah, but. Mm-hmm. No, it's not infinite sum. It's a finite sum, of course. Yeah. It's simply conventional, notational convention. So it's from rational points of algebraic curves over functional fields. Рациональные точки алгебраических кривых над функциональным полем. So this, yeah, in fact, he didn't do such a, no, in this article you see no hypergeometric series, nothing, and only Karl-Fuchs equations. No, even the fact that maybe there are room to get more precise, refined statements in making use of hypergeometric expressions of curves of periods, not on other algebraic varieties. Yeah, I think. Yeah. Maybe Dwork did it somehow, and Bukas some number theorists worked on this direction. Okay, so this is the last statement that I wanted to present for this curve, x to the x minus 1 to x minus t. And now I'd like to pass to the discussion of Gauss-Manning system. Maybe I can raise. I begin new story. So the somehow Yeah, let me introduce this new notation. Xt equals x cubed plus t1x plus t2. That's, instead of consider this family, I consider now a family of elliptic curves. So t, this t. And it's compactification. In fact, there's no need. Yeah, wait a minute. Wait a minute. No. Sorry. Maybe this is the difference. So it's better to consider in a fine part. This curve. Yeah. And so delta t, I denote by delta t discriminant. Discriminant of this this family elliptic curve, that is, say, d so C, I denote by t, ct, the ct0 is singular if and only if t, this parameter, belongs to D, that is, say, delta discriminant be 0. And this discriminant can be calculated in a concrete manner. As you see, that is simply that such t1, t2 choice of t1, t2 such that there is a multiple root for this equation if fx t equals 0. That is, say, t1, t2, if t1, t2 is point belongs to D, then it must satisfy this equation. There must be some x such that and okay, and you can so there exists, that is, a such pair of t1, t2, and the method of elimination method метод исключения. We see that T1 must be, we want to get the equation of delta. 3 times x squared, and T2 is equals to minus x cubed minus T1 times x. That is, say, T1 is already must be of this form. That is, say, plus 3 times x squared times x. I replaced it. That is, say, it's 2 times x cubed. So to get the equation delta t, we need to exclude cube, that is x to the power 6 isn't it? Yeah. And other side we have t2 over 2 the square. Yeah? That also gives us x to the power 6. That is say, in total, we can adopt as d delta t the equation 3 over t1 cube plus 2 square. The point is that, so we have somehow m to the power m type expression and the coefficients. Yeah. And this is somehow certain sense universal. And behind this story there lies the fact that so the period integral is degenerate, it becomes singular. The period integral, that is hypergeometric function. In fact, this is somehow hypergeometric, the reflection of fact of hypergeometric geometricity of period integral. Yeah. That's the maybe right way to understand. So now I need to lemma, prepare lemma, say there exists for delta t, this number x allows an expression, in fact there is a kind of result of division by ideal generated by f and f prime. Or maybe delta x, I write it because there exists b polynomials axt and bxt. In fact, later I will use concrete xt is x square minus 9 t2x plus 4 times t1 square. Such. Unfortunately, I shall use it later to calculate Gauss-Bonnet system. And this is a corollary of very famous theorem that corresponds to the corollary of Weierstrass preparation theorem. That tells us that if x two polynomials, in fact it's x, we are in one variable, but it can be generalized. In any case, it's one variable. No? X is one variable. No common factor. then there exists alpha, beta, two polynomials such that and there is one polynomial in T. You can consider the deformation parameter kind of. You can consider it as a family of polynomials with deformation, one variable polynomials with deformation parameter T, such that alpha times F plus beta times G equals, so they are all in depends on X. But on the right hand side you get polynomial only in T. So I'll leave it as an exercise. So I give you maybe in.
This statement is also called.
Also what?
It's called. So you call this wire stress preparation.
No, it's a consequence of. Consequence. You use wire stress preparation theorem to prove this. It's a division of some polynomial by these polynomial. Huh?
Am I right that the use of this theorem would yield like formal power series?
Yes, it's also true, yes. But I need to pass to local ring, yes. It's also this, yeah, you're right, yes. Of course. You can take it OC, I don't know, so, and X and T, and then you can localize, yes, situation, yes. You can consider local situation, local. Or instead of this is to Cx times one variable times Ct something, yeah, some m, yeah. That's also, so everything can be replaced, and that's also true, yeah. It's, in fact, this has been done by Malgon, okay, that's all, maybe. It's deformation parameter at the wire stress maybe had, I don't remember, so I'm afraid that I say something wrong, yeah. So there is a story of, after that Malgon that's passed to C infinity category, yeah, this. This is Tata lecture by Malgon, and on there is a book translated in Russian, and you can find this statement. Okay, so today, but we need only so simply I want to show you that this expression is somehow stupid, not stupid only stupid calculation, but rather somehow this kind of this relation arises from some background, yeah, background.
I think that comes from Gauss.
Yeah, I think so. Yes, I think so. It's possible. Yeah, it's possible. But Weierstrass, yeah, who proved who looked at this structure first time, and it's a difficult question. But yeah, Weierstrass looked at quite in general situation. Yeah. Okay, and now in making use of this, next is a proposition that consider ring delta. This delta is this now for define our delta ring of rational wait a minute. Yeah, our T is, okay, P is, and the M something, maybe, yeah. This kind of ring. For a ring, we have, no, I don't think, wait a minute. No, X does not have it. Maybe yes. Somehow, maybe I confused some notation. And the R delta so polynomial ring generated by all possible polynomial expressions in X and f 1 over f. 1 over f, f is this. Okay. And dx, consider rational no, ring of rational differential one forms, y goes f. That is isomorphic to, it is generated by only two forms, modulo d exact form, or delta that's the statement. So consider every possible, all possible differential one form. Differential one form, say, that is obtained as a multiplication of this. So first, holomorphic. This was holomorphic form, and times something, yeah. It's rational expression, and this in X. Then it is. If you want, you can imagine that the this ring, yeah, the same thing, yeah. Modulo. Okay. So it is not ideal, yeah. So this is only two representatives in this modulo space. So the proof consists of two steps. So there are enormous, infinitely many differential forms with respect to x and power f to the power
What is d of, is this d
differential with respect to x?
Yes.
X, of course. Yeah. Dx, yeah. No, not t. So first, the reduction to get, how to say, reduction first I reduce this, it as f to the power p plus 1 over 2 over g something, this kind of expression we have, p, this piece is completely different from this. So p, every number, positive integer, this kind of okay, reduce this g over f to the power p plus 1 over 2 equals something g tilde f 1 over 2. Image dx. That's the first. But to do this, it's enough to do. We show that for every g, that is, p becomes p minus 1. The order of numerator decreases more.
We mean by f to the power 1/2, we mean just y.
Yes, it's y, yeah. Yeah, but to see this, because I will manipulate with this f, somehow this kind of relation, so it's better to use f rather than y. It's very easy to pass to y. Yeah? Mm? Okay, so the point is I use this relation. So mod, we show mod and let us deform this expression into especially and times fp plus 1 over 2. Simply I replace the delta t, so delta t of g a f, oh no, f f. I want to use f and f prime. Okay, f prime is f. With respect to f. So immediately you see that already here a times delta times f p minus 1 over 2, 1/2. So this part only we have lesser degree. Yeah? The problem, so this part I deform by in this manner. Apply, of course, plus okay. I will use this later, so I hope that I'm right with this point also. Minus 1 over delta times okay, so this part I will write separately. This additional term is equals to delta F it's simply kind of integration by parts procedure. So, if we consider the derivative bg times f to the power minus p plus 1 over 1/2, then we get first, this one, huh? gb times f prime. gb times f prime, I will have it. That now this dx derivative of this will be, and divided by this will be f prime over f to the power p plus 1 over 2. This. And dx of bg is here. bg is here. So everything is written down here and something. Yeah, in any case, so maybe somehow parenthesis is erroneously put, but the point is that this is this part this is exactly d of dx of this part belongs to dx r delta one over y dx what is it, right? Yeah, something is, no, slightly, maybe I need to add here also, rather this as a differential. In any case, some exact form. This will give us exact form. This part. That is say, and the remaining part will have only with respect to f, so f to the this and this. So the order has reduced, has descended, decreased by 1. Okay? We started from p plus 1 over 2 this, with denominator this power, and modulo d exact form we got so if you take dx, then I get some exact form that is that reduced to p minus 1 to 1 over 2. That is the p has decreased by 1. So we can do it in continuing this procedure till the moment when as it becomes f to the power 1 over 2. That's the first reduction of the power of the denominator. So the second part it's reduction of this g numerator numerator. So now we have let's say g every it's f1 over 2 something, h. And now h okay, I write it here for some polynomial in x. This can be higher order, but in fact I consider division q times f prime is relative with x. More concretely, you can consider 3 times x2 plus t1 plus rx, and degree of r, degree in x of r is smaller than, strictly smaller than 2. That is say it's some expression r0 plus r1x, r0 r1 of some function in t. That's division. Isn't it? So r with q and r so now I want to show that this is for any h of this ring, this polynomial ring, I have okay, well, r1 plus r2 x f over 1 over 2 mod image dx. So first I reduce the power of denominator. Now I reduce the power of numerator to x by making use of this relation. In fact, it is somehow a residue of after division by f prime. So this procedure is maybe quite subtle. So this fact, this is nothing, so it's like a Euclid algorithm, isn't it? PQQ QNF prime. So 2 is degree of f prime in degree in x of f prime, yeah, 3x squared, yeah. So to pass from this expression to this expression, I deform. So q f prime f 1/2 plus f 1/2 r. But this is already done. This is a part of a kind of this kind of expression, isn't it? So the point is to deform this f prime over square root of f 2 times, and to do this, I again two times q dx of f, yeah, yeah, that's the same thing. Yeah, that is dx to q times f minus, that's somehow before I did q. Yeah, so this cancels, and here remains expression that will give rise to exact form, isn't it? So the point is to deform this part, dx, isn't it? And now a bit, so we will concentrate our attention to this deformation of this expression. Yeah. So now this expression I deform by in adding some or so everything is a modulo dx image dx. So I'm authorized to add some polynomial expression q tilde from our delta x to get the equivalent integrand, yeah. So yeah, here it is a bit okay, so dx of q tilde, I think that it is not so q f 1/2. I calculate this derivative, that is say dx 2q times this part and minus q tilde minus q tilde and another. So numerator is something like that. Huh? So what it is, dx. Yeah, here I have, so this will become 1/2 f prime f 1/2. F 1/2, yeah. F1, what am I writing? No, there is no, sorry, no demerit, no, itself, yeah. Q, no, something is wrong, because this one, what is it? Well, there's something wrong. No, it's not true. It's not true. Because, so we have this expression, and dx 2q times dx 2q times. So this is legitimate, and something like this is legitimate. But this must remain, dx 2q this must remain, yeah. Is it true? No, something is wrong. Q f prime 1 and then say, no, that sorry. Here I made a mistake. This is itself. so it is dq dx simply it's a question of question of yeah, that's all. That's all. Yeah, that's all. Okay, so to finish the proof, a bit remained some small portion, but I'm afraid that I will again make some stupid mistakes. Not to confuse you, I stop now. Even though the proof is so, the main point is this. But the argument is not exactly the repetition of this argument. This argument. It is more subtle. Yeah. So the choice of Q tilde. The choice of Q tilde. Yeah. What is Q tilde? So 2Q, no, it's 2.
Did we somehow assume that the differential of our form is zero?
Is?
No.
No. It gives really non-trivial forms. This is the basis of the most integral. So the corollary will be, corollary of this proposition will be to consider any kind of f to the power p minus would be summation of some a1 such that a1 these are also delta over 1 and t. C. So as
Any of these forms, does any of these forms have pole?
Forms have, what do you mean by which form?
Dx over y and x dx.
X over y. So it's holomorphic, isn't it?
Yeah, and the second one is not. So we integrate any form or not any form?
Not any form, but it's in C2. So at infinity it may have pole, but if we exclude, if you consider only affine part.
That's not of any order, just one.
No, any order, gx. Any order, yeah. No, the reduction of order of this part shall be done here. Shall be done here with the aid of division by this f prime. Yeah. What remains is this. Of course, if t is constant, it's relatively easy. No, in fact, it is deformation of the case with constant coefficient case. But a bit careful about the additional parameter. That's all. Yeah. In fact, everything is only dx, only in derivative with respect to x comes into play. So, okay, next time I continue. I finish this and finish this. And derive Gauss-Monnet system. Yeah, next time I will, finally, I finish this introductory part. So dt1, dt2, dt1 I, so let me gamma y dx x dx. Consider this two forms, and so I equals something coefficient times I, and 1 over delta t times some. In fact, it is for both. I get this Gauss-Monnet system. So our aim will be this, and this system of differential equations, it can be written down like d di. Now this is in t. With respect to t, I have equals omega times it, differential form, some 2 times 2 matrix with even log d. So one form along with logarithm with singularity with poles, first order poles, along d, that is delta t equals 0. So this is Puff equation, Puff form equation, that is equivalent to this Gauss-Monnet system. That I will discuss. So this will be the end of the presentation on elliptic curves, and that can be generalized to quite more complicated cases. Yeah. And every story shall be somehow generalized, including hypergeometric representation. Okay, so